Good morning, I'm Sarah Jane Schmidt, and in this video, I'll be talking about my paper, Characterizing a Dramatic 9-magnitude flare on an ultracool dwarf found by the ASAS-SN Survey. The All-Sky Automated Survey for Supernovae uses these twin 14-centimeter telescopes to image the sky once every 5 nights in V-band. On August 14, 2013, ASAS-SN detected a dramatic transient which faded in confirmation images taken 2 hours later. A cross-match to the Sloan Digital Sky Survey photometric database indicated the source was a cool, faint object. Follow-up spectroscopy in both the optical and infrared, shown here, confirm a spectral type of M8 for this object named SDSS-J0221. The M8 spectral class includes both brown dwarfs, which are usually younger than about a gigayear, and stars, which are usually older. Because magnetic activity could indicate youth, we examined the spectra for features consistent with low gravity or very young objects. We found no low gravity features, and the kinematics of this object are not consistent with membership in any young associations or moving groups. SDSS-J0221 could still be a young object and could still be a brown dwarf, but it remains undetermined. In addition to characterizing the source, we also examined the flare. First, we'll look at the flare light curve, shown here in terms of delta V magnitude as a function of time since peak detection. If you're not used to working with delta V, fainter's on the bottom, brighter's on the top. In the inset, I'm showing the entire range of magnitudes, including 0, which is the quiescent magnitude. To understand the entire energy of the flare, I need to fit a model, so I've chosen a simple classical flare model. It begins with a linear rise, and then transitions to a linear decay, fitting the first 2 points. Taken together, this is known as the impulsive phase. After the impulsive phase, we transition to the gradual phase, well modeled by an exponential decay. Since each flare is different in the length of its impulsive and gradual phases, we use a family of models, all consistent with the data, to understand the range of properties consistent with this flare. The average integrated V-band energy of these models is 5 × 10⁻30 ergs. Converted to U-band energy, this is 10⁻31 ergs. That's a few orders of magnitude less than the largest flares on mid-M-dwarfs, but still very large for an ultracool dwarf. Next, we'll look at the emission mechanisms of the flare. Here's an M8 spectrum calibrated to the quiescent magnitudes of SDSS-J0221. A major contributor to flare emission is a blackbody component. So to reproduce the peak delta V magnitude, we use 3 blackbody curves of 10,000, 13,000, and 16,000 degrees Kelvin. Each of these curves would cover from 11% to 34% of the area of the star to reproduce the entire V-band emission. This area coverage is very large compared to other mid-M-dwarf flares, whose peaks typically cover 1/10 the area that these do. We also looked at the gradual phase detection, reproducing it with 7,000 and 10,000 degree blackbody curves, corresponding to respectively 3% and 1% of the surface area of the star. This dramatic change between large area and smaller area is typical of detected flares. So to sum up, we have a very large flare, both in terms of delta magnitude and energy for an ultracool dwarf. The flare energy is not as large when compared to classic mid-M-dwarf flares. At its peak, this flare covered a large surface area or had a very hot characteristic temperature. For more details, please check out our paper on the archive. Thanks.